We present our work titled Robust 3D Garment Digitization from Monocular 2D Images for 3D Virtual Try-On Systems, done jointly by Myntra Designs and IIIT-Hyderabad. We can try out garments in a shop, but what if we can virtualize this experience? Our goal is to generate textured 3D template meshes of 2D clothing images from real-world fashion catalog images. These template meshes are then draped on a human avatar to enable a virtual try-on system. There are a few challenges of enabling a 3D garment digitization solution from existing e-commerce catalog images. Our proposed pipeline is robust to handle such major challenges, which include occlusions of the clothing texture by body parts and large body pose variations. Additionally, our method does not expect any constraints on clothing images such as segmented images of clothing without humans. Our proposed pipeline includes 3 modules. We first predict a sparse set of 2D landmarks on the boundary of garments in the image. These landmarks are used to perform a Thin-Plate-Spline-based texture transfer on UV map panels. However, due to view variations and self-occlusions, these UV maps have large holes and missing parts. Hence, we employ a deep texture inpainting network which inpaints relevant texture to generate consistent UV maps. The 3D models for clothing are then draped on the target pose of 3D human avatars to enable a virtual try-on system. In order to train our models, we generated synthetic data and rendered the images in a way that resembles an e-commerce catalog. Each generated image is paired with segmentation maps and landmark annotations. We show some sample images from our synthetic data which are generated by using a large variation of textures, poses, and lighting setups. For our landmark detection module, we use a multitask learning network to jointly predict landmarks and semantic maps. Although we use both tasks for subsequent stages, we focus on the landmark prediction task, since the texture mapping module is heavily influenced by the pixel-level alignment of the landmarks compared to the semantic maps. The landmark detection network is evaluated quantitatively using the normalized mean squared error. We trained our model with 250, 500 and 1000 real-world training images in Scratch and fine-tune settings. A fine-tune setting represents a model first trained on 5000 synthetic images and then fine-tuned on real-world data. We can observe that fine-tune 250 outperforms Scratch 1000, thereby establishing the fact that training on synthetic data significantly improves the performances while reducing the dependence on expensive manually annotated real-world data. Our texture mapping module takes predicted landmarks as input and maps the relevant regions of the 2D image onto the UV map of the template garment mesh. The TPS-based texture transfer module preserves the fine texture details and avoids loss in texture quality. The deep texture and painting module helps handle the challenge of clothing textures that are occluded by body parts. We show a few qualitative results of the texture and painting network on synthetic data and real-world data. We make a qualitative comparison with state-of-the-art methods. As can be seen in the first row, PIFU and Pix2Surf failed to preserve the high-frequency texture details. The bottom row shows that unlike PIFU and Pix2Surf, our method can handle self-occlusions. After we obtain a textured template mesh for clothing, each mesh is aligned with avatar in a T-pose. The cloth mesh is deformed to the desired pose using a physics-based cloth simulation. We finally show a video example of how such digitization will facilitate a 3D VT system. To render a 360-degree view of garments. On realistic custom avatars with different body shapes.